So continuing our discussion about volumes by slicing, we in the previous video talked about disks, where if you look carefully, you'll see that the shaded region was attached to the axis of rotation that entire way across the interval from A to B. So that happened again here in our example 1. And then when we went to rotating around a vertical axis, same concept. We have this axis of rotation here, and the shaded region, which was over here on the right side, was completely attached to it. Right? There was no space, there was no daylight between them. Same thing here. Here's the axis of rotation, and the shaded yellow region is attached. Well, what if it's detached? That's where washers come in. So moving on to our washers discussion, we have a couple of functions here. Here's the generic setup. We have a couple of functions, and they are separated by a little bit of space right here. So you can go ahead and connect those right there. But then recognize you will be shading this region right here. We'll do that lightly. So that region will be rotated around the x-axis. It says so right over here. So what we're going to do to get this going, let me use some different colors here. I'm going to grab this top right point, and I'm going to rotate, which basically makes it go down here. And then it would rotate back to the top. You can do the same thing on the inside point. That would go out and down and back, and that was an awful picture there. So let me try that again. So this one came back up like so, and this one comes down. You're just drawing a little oval, a little ellipse, if you will. And this right here on the left side, this is where maybe you want to have the thickness grow a little bit, just so you give a little bit more of a 3D feel. So that's in the foreground. Okay, this is in the background, back over here on the right. So foreground's on the front over here. So let's do the same thing on the left. Upper left ends up down here at the lower left. I'm going to give that some thickness. That was not very clean. Give it a little bit of thickness to the inside one. Do the same thing. So there we go. And we don't need a perfect picture. Keep that in mind. This is just a quick picture. Nothing crazy here. You just need to understand the concept. You need to understand where things are and what they're doing. And then we'll set up your equation or your integral, and we'll be good to go. Okay, so there are actually some a and b values. We're going to go from a over here to b over there. We need to go find the radii. Now the radii, let me label them right here. There's the big radius. We'll call that big R. And then we got the little radius. That's little r. So the big radius is from the axis of rotation out to the far side. So that would just be f of x. Now technically it's minus 0. And we know minus 0 doesn't do anything, but we should be thinking of that just in case that second function is not the x-axis. Next up, the small radius, that would be g of x. And again, minus 0. So doing what we did before, we want to set up a volume formula. We know there's going to be a pi r squared involved, but this time there's a big pi r squared from A to B, and then there's a smaller pi r squared, still from A to B. In effect, what we're doing is we're integrating up and down like this, getting the entire big area, and then when we're done with that, we're going to go integrate the smaller, oops, I meant to change that back to green. There we go. Then we're going to integrate the lower area down here, and we're going to subtract it out. If you subtract out that green section I just did, from the bigger section that I started with, which was this one, what you're going to be left with is basically the outer volume, which is exactly what we need. All right, so let's go ahead and do that. You'll notice down here we have two integrals, but they share a lot. They have a lot in common. They both are going from A to B. They both have a pi in it. They both have a dx. The only difference is the r squareds. So we're going to bring that down here. We're going to say volume equals, bring the pi out front, A to B, and we're going to factor out that pi. It's out here. We're also factoring out the dx off to the right side. So you bring the pi out, you bring the dx out, and you're left with big r squared minus little r squared. And that turns into, if we use the actual functions, that would be f of x quantity squared minus g of x quantity squared. And we'll throw some parentheses around there and throw the dx out back. All right, that would be a great place to throw some color onto your page. Specifically, volume is going to be first function squared minus second function squared, and the first function should be the upper function. And over here, we're expanding on this idea of we find the area of the big circle, and then find the area of the small circle. And then if you wanted to, you could factor out the pi and leave the r squared minus the other r squared. Okay, so that's a two-dimensional thing over here. And then over here, this is a three-dimensional thing. All right, so now we have volume involved. Okay, let's go on to example 3 and actually see how this works. So it says, find the volume of the solid generated when the region between f of x equals 1/2 plus x squared and g of x equals x over the interval 0 to 2 is revolved around the x-axis. First thing we'll do is start out with a little graph. And I've kind of mapped this out already in my head. I was thinking of the 0 and the 2. 0 will get you a 1/2, 2 will get you a 4.5. And then for the other function g, it'll just get you a 0 and a 2. So if we go up to 6, that'll be plenty high enough. So we'll go 6, 4, 2, and then this would be the x-axis. So there's the x-axis. Here's the y-axis. And we are rotating around the x-axis. It says so right here. So let me get some colors going here. How about some purple? For the line, I'll do the line first because I think that's easier. Oh, I forgot to scale my x-axis. So let's go like 1 and a 2 and a 3 and a 4. I think that'll cover it. In fact, let me do that again. I'm going to space them out a little bit further. That's fine. So we'll go 1 and 2 and 3 and 4. Here's a 2, here's a 4. So now let's go sketch the graph. So 1, 1 would be here, 2, 2 would be here, 3, 3 would be there, 4, 4 somewhere out there, and of course 0, 0. So we're looking for a straight line. Use your imagination if it doesn't look straight. Okay, there we go. So that is g of x equals x. So now for the other curve, how about some orange? So if you plug in 0, you get a half. If you plug in 1, you get 1.5, because you square the 1 and add a half. If you plug in 2, you get 4.5, which is about right there. And keep in mind it's a parabola, so we know the shape. It's supposed to go looking like something like that. There we go. And that's f of x equals the 1/2 plus x squared. All right, so now let's look at the region that we're supposed to be rotating around. It says from 0 to 2, so I'm going to stop it here. It starts here. If I just shade this lightly quickly, that's what's going to be rotated around the x-axis. Now you'll notice it is detached. It may be attached to the axis here, but it is detached over here. That means there's daylight. That means it's not really a solid figure. So that means we will be using washers. Okay, let's go find the two radii. I'll throw it in with some blue like we did last time. Here's big R and then little r. So big R is going to be the f of x minus 0, which is 1/2 plus x squared minus 0. We don't need to write the minus 0 because it's not doing anything. And then little r is going to be the g of x function minus 0, which is simply, what is that, x? Yeah. So that's just x minus 0. All right, it's time. Let's go use our formula. Again, there's not much to it. All you got to do is put a pi out front. We're going to integrate from 0 to 2, of course. That's your interval. And then we're going to have the first function, which is 1/2 plus x squared. That's your big R. Square it. Minus the little r. Square it. And then we'll throw a dx out back. All right, it's time to go ahead and FOIL that out. When you FOIL out, be careful. We need to make sure that you FOIL this carefully. This is a 1/4 plus, here, let me write it over here so you can see it. If you multiply that by itself, you get the first terms, then the outer, then the inner, and then the last. So it's 1/4 plus a half x squared plus another half x squared, which gets me a whole x squared, and then we have an x to the 4th. And then we can subtract out the x squared, which was that second function squared. Cleaning this up a little bit more, we're going to have a 1/4. The x squareds actually cancel each other out because we had 1 plus 1 minus. So we have a fairly nice integral that we can go find the antiderivative of. So let's see here. Oh, I guess I don't need that anymore. I'm ready. I just need to go find the antiderivative. So that means 1/4. Don't forget the pi out front. 1/4. Nope. Just kidding. Just keep making mistakes here. I'll get it. 1/5 x to the 5th. Nope. I'm thinking of the second term. Can I get an it's cool? All right, here we go. 1/4 was a constant, so throw an x on it. Then we have the 1/5 x to the 5th. That's what I wanted to do a minute ago. And then we're integrating from 0 to 2. So 1/4 of x plus 1/5 x to the 5th. All right, I think we're ready now. I think I'm done with my mistakes. All right, we'll leave the pi out front. We're going to plug in the 2 first. Not because it's bigger, but because it's on top. Top goes in first every single time. I like to parenthesize that every single time, and then we'll go plug in the second value. And we love our zeros, but make absolutely certain that they really do zero out those terms right there. Be careful. All right, so we got a pi, and we're going to have a 1/4 of 2, which is 2/4, which is 1/2. 2 to the 5th, you should know, is 32. Use your hand, right? 2 times 2 times 2 times 2 times 2, 32. So we have 1/2 plus 32/5. And then it would be good to go make these into common denominators. So we'll do that right here. So we get pi out front, and we're going to get 5 plus 64/10. So that turns into 69 pi over 10. Excuse me. You could also write 69/10 of pi. If you put this in the calculator without the pi, you'll get a 6.9, and then you can attach the pi. You can get a crazy decimal answer. There are lots of options there. All right, that's it. All right. For our fourth and final example, we are going to talk about other axes of rotation. So if you need to pause it for a second to copy down the example over here on the left, here's our example 4. It says to find the volume of the solid generated by rotating y equals x squared, our mother function for all parabolas, about y equals -1 on 0 to 2. So pretty basic function. We got a simple y equals -1 line. It's a nice interval from 0 to 2, nothing crazy, no weird numbers. So here's how that's going to work. Let's see, we know y equals x squared looks something like this. Okay, we only need the right side of this because we're going from 0 to 2. So if that's 0 and this is 2 over here, we're only looking at this region right here. And then we're not rotating around this x-axis. Let me label my axes real quick. This is x, this is y. We are not rotating around x. We are rotating around or about y equals -1. Let me draw that in down here. I like to draw the axis of rotation as a dashed line so it stands out, looks a little different. And that would be good to help your teacher out too, so they can tell which one's the x-axis, which one's not. Okay, label the axes and label your axis of rotation as well. So now we're going to take this shaded region right here. Let me throw some pink shaded right here. We're going to shade that region, which by the way is detached from the axis of rotation. We're going to rotate it around this y equals -1. Okay, so let's think about that for a second. If we're going around y equals -1, we have 2 radii I see right here. We've got this one here, that would be the big radius, and then we got the small radius. Okay, so just like we did on example 3, because it's washers, because it's detached, and this one is fully detached, it's not just partially detached, we need 2 radii. So Let's make sure we're really good about labeling everything, including our function up here is y equals x squared. We've labeled our big R. We've labeled our little r. Little r, and coincidentally, is just not going to change. It's always 2 units. So no, it's 1 unit away. Excuse me. It's 1 unit to get from 0 down to -1. So let's go write out our radii. I like to write these down before I set up my integral. It's going to be the high function minus the low function, which happens to be your y equals -1. And of course, that turns into a really nice x squared plus 1. For little r, we're going to take the high, which is 0, and subtract -1, which of course turns into 1, because we know the distance here, it's always 1, right? There's nothing changing there, because it's 2 parallel lines. Okay, I think we're ready. We just need a big R squared and a little r squared to throw into the integral. So here we go, volume equals pi from 0 to 2. We're going to go big R squared, which is x squared plus 1 squared, minus the 1 squared, and then we'll throw a dx out back. All right, so there's the integral. If this is a calculator question, you are basically done. Put that into your calculator, do your Math 9 thing, whatever you got to do, get that integrated, attach a pi to it. You can even get it into a nice fraction form if you'd like. We're going to do this by hand here, just good practice. First thing I want to do is go ahead and FOIL this out. I'm not going to belabor that point. I'm just going to do it. X squared squared will be an x to the 4th. Then you're going to have an x squared times 1 and a 1 times x squared. That'll be 2 of those x squareds. Then you have a 1 times 1, which is a plus 1. Then you have a minus 1. And these immediately, I notice, will cancel each other out. All right, so let's go ahead and close up the parentheses. And we'll rewrite this. It's 0 to 2. We have just x to the 4th plus 2x squared with the dx to close it up. And we need to integrate now. So, a little review of integration. We have to raise the power on the 4, so that'll be a 5. You then divide by a 5, or you multiply by the reciprocal of 5, which is 1/5. Next, you have a 2. Your x squared will become an x cubed. I'm going to go put a 1/3 in front of that. So we have 1/5 x to the 5th plus 2/3 x to the 3rd. Do not put a plus c because this is not an indefinite integral. This is a definite integral with a 2 and a 0 ready to get plugged in. So let's do that. Pi out front, we're going to go 1/5 of 2 to the 5th plus 2/3 of 2 to the 3rd. Put those in parentheses. Subtract your second number going in. We love our zeros so much. That's going to go away. This will also go away. Be careful when you're plugging in 0. There's a tendency for students to cancel out 0 terms no matter what. But if there was a cosine 0, that's equal to 1. That doesn't get canceled, right? That should not get canceled. The answer is 1. If you had an e to the 0, also not time to cancel. It's a 1. There are plenty of other functions, but those are the 2 common ones that come up fairly often. So be careful. But for us, these really do cancel, and we're happy about that. We have a 32/5 here, and then we have 8 times 2. 2 to the 3rd is 8. 8 times 2, that's a 16/3. And it's just time to go get a common denominator. Pretty easy. We'll go get 15 as our common denominator. So that's going to turn into, let's see, 96 plus, let's see, 16 times 5 would be 50 plus 30. That's going to be an 80. That's all over 15, and we'll attach a pi to it. Final answer, 176 pi over 15. Great final answer. If you're going to put this in the calculator, and you've got the old school calculator set up, when you do your integration, do not put the pi here. I do recommend you put them into your calculator as y1 and y2. Let me show you what I mean by that. This to me is y1 squared minus y2, y2 squared. So y1 is x squared plus 1. That's actually not one of our functions, but it's a combination of functions. But it'll speed us up when we go to the calculator. So then we can pull up y1 squared minus y2 squared, comma x, comma 0, comma 2. And when you're done, you're going to get a weird decimal. and then you can go like this. You can go math, enter, enter. That'll get you a nice fraction, 176 over 15, and then you attach the pi to that. Okay, don't forget to attach the pi. Final answer is 176 pi over 15. Okay, quick reminder, when you have this daylight in between, when it's detached in any way, you will be using washers. This one was completely detached. Let's go back. I apologize for the crazy scrolling. Let me get back to the page where I had just calculated this. If you have any detachment, there's some detachment there. Now it is attached right here, but it is detached over here. Okay? So if there's any detachment, you're going to see two radii, big radius and small radius. All right, hopefully you caught all of that. Feel free to go back and watch whatever parts you need to watch again, and we'll see you next time.